Okay, so we had our proof of what brings a ferromagnetic material through the top of the hysteresis loop, and the fact that after you remove the magnetic field, you keep a sort of magnetic remnants. So our steel scissors we brought them up here, and then we removed the external magnetic field. They retained a certain level of magnetic capability. So there was a stored alignment of the magnetic domains inside that gave rise to an overall magnetization that made the material itself magnetic, meaning capable, not only ferromagnetic, but capable of attracting other metals in the field. Something that has a slightly same hysteresis behavior but less pronounced would be the very soft ferrite magnets. So depending on how your material behave, you can have an hysteresis loop that is still an hysteresis, but the moment you remove the magnetic field, your remanence is way lower. And instead, you can have magnetic materials that, when you remove the magnetic field, they retain an incredible amount of magnetization, and it's much more difficult to shift them. This is the difference between a hard magnetic material and a soft magnetic material. A hard magnet will have a much stronger behavior as a magnet. So the little blue thing that I used before is most likely a barium or a strontium ferrite material, so a very strong magnet. But even something a lower capability, depending on the strength that you need, will have different capabilities. So now we're going to go through different type of ferromagnetic materials and their relative behavior in terms of delay and ability to keep the field line densified inside. So soft magnetic materials are, for instance, magnetite. So the original magnetic material in reality doesn't have a very impressive hysteresis loop. It's very easy to magnetize, and it doesn't keep a very huge remanence, and yet it was the original magnetic material. So this is still a relevant effect. It's just weaker in comparison to others. So the representation here is that it's easy to magnetize, the remanence is low, the easiness of magnetization comes from the incredibly low coercivity. So if you switch the field, you can just magnetize everything in the other direction. So you have a field in one direction, we follow in that direction. You switch the field, we follow in that direction. We don't oppose a lot of resistance. So this happens in iron 304, but it also happens in some iron silicon alloys. So there is very little dissipation of energy. The switching is done fast. The energy that you keep is just there. You can just move it up and down. This material by themselves, they can also create a shielding from magnetic field. Why? Because if you impose an external magnetic field and you have a ring of a material that has this very, 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 very easy allowance for densifying the field light, because it will just follow through any field that is provided, it means that you densify everything to follow inside the material. By the time you exit the material, nothing managed to come inside, because everything was actually channeled by the material to realign all the magnetic domains. So what is the difference between a soft magnetic material that is still a magnet if you magnetize it, because we know that the lodestone still works plenty, and a hard magnetic material? A hard magnetic material is more difficult to magnetize. You need to put more effort to bring it into saturation, but once you do it, it will have a high coercivity coming back. So you need to put more applied field to be able to go to the right point. And if you try to switch, the first thing that you will notice is that there will be a high coercivity. The second thing that you will notice is that if you remove the field, you keep a very high saturation. So this is a high remanence, and this is high coercivity, meaning that a zero field, after bringing it to saturation, it will retain a lot of the magnetization, so every energy that you put is stored inside of the material. If you try to switch it, it will dissipate a lot of the magnetic energy that you put from the outside to persuade itself to just switch direction until it goes into the other part. So the dissipation here is inevitable. Whatever energy you put from the outside will actually have to go through this process, but it also means that you have a storage. So there is, when you magnetize your material, you put the effort of putting a magnetic field on, but then your material is retaining this strength. It's not going to bring it out. It's an energy that you store. It's an energy that comes from the electromagnetism. So as we see, you can make a magnet do stuff by nature of having a magnetization stored inside. And this energy can be quantified with this thing that is called the BH max. So this square that you can put under your hysteresis curve. If your hysteresis curve were to be a perfect rectangle, so you lose zero magnetization, you have a huge coercivity, and then you go down, this BH max will be massive, and that will be an amazing and incredibly hard material. So these things are the ones that you really use as permanent magnet, meaning that you put the effort to magnetize them at the beginning, and then you assume that they are going to stay magnetized. So when you think about a magnet, in reality you're talking about a permanent magnet, a ferromagnetic material below its Curie temperature that has been magnetized. Now, some of the very common magnetic materials tend to be alloy, just by nature that you can have a lot of magnetic atoms inside. And one of the very common one is the Alnico alloys. So these are your usual completely metallic material. They are even bought in bulk, and they've been around for a very long while. So since 1932 there has been a lot of tweaking of composition, and you can see that the Alnico is basically aluminum, nickel, cobalt, copper, titanium, and for a lot of this, so not all of this material, but a lot of this material will have free magnetic moments that then you can make go through, they will go by their own nature through a ferromagnetic order, and then you can align with the field. You have a huge BX match and a remanence that keeps, after you align, you remain with 1 Tesla of magnetic field inside, and it can be, the coercivity can be tuned with the composition, but is high. So this thing, by nature of having a Curie temperature of 800 degrees, so it's higher than 800 degrees, meaning that if you keep your material operating because it's doing stuff up to 500 degrees, it's fine. It will behave like a magnet, and there is nothing you can do about it. Now, the alloy here, and the trick that allows you to tune a lot of these huge effects, is that you have 2 isolated phases. So by itself, you would make your Alnico in a normal ferromagnetic but not magnetized configuration in the alpha form. When you heat up and you apply magnetic field, you start to make 2 different nano phases, the alpha 1 and the alpha 2. And the resulting property depend on how anisotropic these phases are from each other, so how they are not like a nice sphere, they are a bit weird of a shape, and what is the difference of magnetization of these two phases, because they will be the phases in which you actually have all the domains aligned. If you manage to do this very nicely, then you will have better properties. So this tweaking of composition that gives you higher remanence, higher coercivity, is because of this demixing type of business of nano phases inside of the material. But this is something that you can control with composition. You don't have a very precise control on the structure, because it's the mixture in the same crystal structure going into two different sort of magnetic phase segregation. When you want to improve it a lot, you want a lot more control on what is going on. And the best permanent magnet available at this state of the art, is magnets that are based on rare earth. So usually neodymium or samarium based alloys will have a specific crystal structure that help them actually have the best magnetic performance in permanent magnets. So samarium based alloys were first developed in 1960s, so it's a good 30 years of development of magnetic materials. And they have, again, a very high Curie temperature, so you can use them at very high operational temperature of whatever you're using, and will be corrosive resistant, incredibly higher BH max, so this thing will actually look way more like a square than just like a smooth drop. And usually you have rhombohedral or hexagonal forms, depending on the samarium cobalt ratio between the two. The structure look actually very nice, and the trick here is that you have a lot of magnetic atoms, so atoms that have a magnetic moment by themselves. They order themselves ferromagnetically, and they order themselves ferromagnetically following a very specific anisotropic arrangement. Can you see this nice basically stars of arrangement of the atoms? This can be sort of replicated even with more stuff when you have the neodymium. So these were relatively recent in terms of development in science, in the 1980s. High in Curie temperature, but way higher, like this is almost double the samarium one. Once again, why? Because you have a series, so it's not only neodymium iron, but you have a series of different positions in the material in which you find a series of magnetic atoms. Don't worry about these things. These are crystallographic notation that you're not supposed to know at the moment. But what is nice here is that if you notice how we shape this thing, not only they align antiferromagnetically, but they have an inherently anisotropic form. So the most common crystal here is the Trigonal Crystal, so that the Trigonal Crystal already has a longer axis, and by their nature, for the way they are arranged as magnetic atoms, when they sense each other and they align ferromagnetically with each other, you end up having them already through the single unit cell, coherent, all in the same direction, which means that there is a prominent anisotropy. They like to go all in one direction in terms of magnetic moment, which means that your single cell will have this thing, so a series of cells will start to have a huge magnetic moment, and once you align all the magnetic domain all together, this thing will come out as a very prominent business. So the neodymium and the samarium based alloys, depending on how you make them, can actually have slightly different behavior. This is fairly common with alloys. So either you sinter them or you do the melt spinning. So these are all tricks that are based on do you bake your material, then you compress it, then you reheat it, or do you actually try to make it under magnetic field, or you try to like mix it with other stuff. Now the trick is that the sintered magnets kind of tend to have a higher remanence. This thing done with melt spinning, and are usually called also bonded magnets, you try to improve some of the shapes that you can give to this with with additional materials. So you can mix polymers, you do shaping. So the good thing about the bonded magnets is that you can have more complex geometry for a good efficiency. For the sintered magnets, you have the true maximum efficiency. So this thing, you mix in stoichiometric ratios, you melt, you cast, you crush, you compress, you anneal. It's a lot of improvement that you need to make, but the material is brittle because it's very strong in terms of magnetization, but if you want the best magnetic properties and also a very good malleability, then you need to add something into your material. So when you want these very peculiar shapes, which might be very interesting engineering speaking, then you need to have something that allows you to mold your material in the right shape without your material cracking in between and making all your efforts useless. So this is something that you kind of need to remember, that these alloys are brittle. They are not your nice steel scissors. They kind of crack very easily. So you often need to coat them. So you made your magnet, you coat it up so that it doesn't flake off and stuff like that. Or you need to mix it with something that is different, so you kind of kill part of the magnetic, the permanent magnetism behavior to be able to shape it better. Now, since they look so nice, the question could be, why are we not using them constantly all over the place? Because they are expensive, and not only they are expensive, but this performance comes at the cost of using rare earths. Now the rare earths are all materials of the F block, so by nature of being in the F block you can have a lot of possible unpaired electrons. This can have very nice magnetic moment behavior of the atoms, so that if you manage to pull together will give you a huge magnetization. But the supply of neodymium, samarium, dysprosium and stuff like that are all not only a scientific issue, they are an economic supply issue. They are difficult to extract, and the price of this thing fluctuates a lot with political leverage. So when you want to look at materials, you always need to look at how feasible it is to make it, how much is this going to cost me, and is this going to be business critical when I try to apply it into something that needs to go in big scale. So if you want something huge that needs a lot of material, but your material is incredibly pricey and the cost can become a political issue, then you might actually find yourself possibly preferring other alternatives that are kind of cheaper. So kind of cheaper and more affordable are usually ferrite magnets. So ferrite magnets are actually transition metal oxide based type of material, incredibly beautiful structure, and you can notice immediately how this structure is anisotropic. So it has a very, very, very long axis in one direction, and the other one are tiny. So you do this huge rectangle with a very long edge, and it's made of cheap constituents. So strontium or barium with iron, with a lot of iron positions, it's fine. You can actually afford it, but by nature of having a series of magnetic moment and an overall net ferromagnetic behavior, you end up having a nice alignment, the preferential alignment of your magnetic moment, the overall magnetic moment of all these atoms ferromagnetic together, will be along the long axis of this cell. And since they're made of cheap components, you might like them, but you need to remember that this is like an order of magnitude of difference of coercivity. And the coercivity comes from the likelihood of you reorienting the magnetic domains. Can we improve the coercivity of a material if we have a better control on the components, so we can actually do a lot of tries? You can actually do that, because the coercivity is basically a function of how your material reacts to the magnetic field. A molecular magnet has no coercivity. It just flips with the field and you just follow it. So you have a magnetic moment, but there is no coercivity. This region can exist also with the material. And if you don't even have the possibility of controlling with field, it just flips with itself, you are in a super paramagnetic behavior. So if your crystallites are so tiny that just a temperature can flip them, then you are in super paramagnetic behavior. There is no way for this thing to permanently align and reach a magnetic order. If they are in a state of magnetic order, then you have this thing of they will start to align. So when you have a single domain, so you have a single material and all of it is aligned in one direction, there are no different domains, it's a single area with all the magnetization. If you increase this size, the coercivity increases up to a maximum. Once you start to make multiple domains, you start to create those area in which you try to align the crystallites in comparison to each other so that they nullify the general magnetic moment. Given these points of transition, with multiple domains, you start to lower the coercivity, because there will be a lot of intermediate points that we call the domain walls that are mediators of this magnetic effect. Now, the domain walls are also called the block walls and are what happens given that you have different domains with different alignments, but you need a point of transition between the two because this is still the same material. So structurally speaking, nothing is changing, but you need the transition point. So this is a point in which you are kind of dissipating energy. The thicker is the domain wall, the easier it is to make the material switch the field, and that's the reason why the coercivity decreases with the increase of the domain size, because in a multiple domain you also have a lot of multiple domain walls, meaning that your material will find a way to just accommodate the field and just go in the direction of the field. So that's the origin of the coercivity behavior. If you had a way to actually stabilize your multiple domain magnetic material, then you will go into a steady maximum of coercivity. This can be done in material, but it really requires you as a chemist figuring out what you want to do. And this is a particular work that has been pioneered by the University of Aarhus, in which I also did my master. And this, what you're doing here is upscaling the anisotropy of your material. So you want to accompany the fact that you have an anisotropic unit cell into an anisotropic big crystallite in which all the shapes are aligned, and bring it into a very huge bulk material. So you want to accompany this overall magnetic moment all the way through. And this is done by nanosizing the powders and then increasing the layering. The standard commercial has this curve over here. If you do this trick, nano-sized and then press, but you press anisotropically, you can see that your curve starts to look like a block. So this is a thing that you can think about as a chemist. How can I bring my material in the shape I want it, with the properties I want it, even before magnetization? So this can even be further improved if you put your material under field. So commercial magnets are always previously magnetized, so this thing is a very nice way to do this. Now, very quickly, why would you want to do this? Because magnets are actually useful for a lot of purpose. And one of the purposes, since we're talking about this in digital environment, is that magnets at this stage are still the best, safest way you can store data. So in a magnetic recording, you basically have a series of magnetic units in which you align the magnetization in one direction or the other direction, and you need 3 components. So you need your storage point, something that reads, and something that writes. And even though there has been the development relatively recently of solid-state drives, these are still the best approach to magnetic storage. So your storage medium needs to be a small magnetized area that keeps your data in forms of magnetization up, magnetization down. Your write head needs to be the thing that generates the magnetic field, that can flip the magnetization of your storage. And your read head is your sensor. So it's the thing that is sensing the magnetic the magnetic orientation of this and bringing a signal. Is it up? Is it down? Is it up? Is it down? And just connects it off. The write head, in its nature, needs to have a very large induced field, but it needs to be easy to switch in direction, because you want to be able to magnetize your storage unit up or down, but it needs to be able to generate both fields. So this needs to have a very high permeability and a low coercivity. And this is the definition of a soft magnetic material. So the write head of a magnetic data storage, which is a hard drive storage usually, are soft ferrites. Significant improvements have been made in terms of arranging these things and making sure that they go on in better arrangement, better timing, because you want to make them smaller and smaller and smaller and more and more and more reactive. So higher saturation will make them better, but you need to be able to switch them. And the high frequency response is the thing that commands how fast can you actually write down data, because you can slide this thing, but this thing, as it slides, will have to go up and down and up and down and up and down and change the magnetization of your data storage points. For the data, you need to store them in up or down configuration. So magnetization up, magnetization down will be the equivalent of having 0, 1, 0, 1, 0, 1. So what you need for your actual storage unit is something that has 2 different perfectly stable possibility of alignments and with strong flux around every data point. Why? Because you also want to be able to read this thing very easily. So you have a very precise, strong signal in 2 very easily distinguishable configurations. So you need a square hysteresis loop and no change below a precise field. And this is the definition of an hard magnetic material. So you know when you're switching it, but since it has a high coercivity, if you put a field that is lower than the one required, your material does not switch. It doesn't care, and it stays in data requirement. So this anisotropic thing is also preferred for the packing, because you want to be able to have nice alignments, and you can pack a lot of them just very nicely squished together. The lower the size, the higher is the disk capacity. But of course, the smaller you make the particles, the more you might go off that point in which your material actually displays a coercivity behavior. We just saw that. So you need to be careful not to end up in the superparamagnetic point, because it means that at that point your material is not flipping, is not keeping the magnetization, it will flip by itself. So this square hysteresis loop is lost. And you might have the issue, as you go lower and lower in size, that having a series of materials, magnetic materials, aligned with each other, with a certain field inside, with a field that you want to be strong, might influence each other. So if the particles are too small, you might be able to pack a lot of data, but you might have a lot of errors, because you might have a basic issue of particles sensing each other and changing the permanent magnetic field. So this is the key of additional development. But if you've seen the development of HDDs in the last years, you know that you can fundamentally pack 5 terabytes of data in something that a few years ago could only keep 230 gigabytes. So it is a strong improvement of the field. So this is a general idea of what you can actually have in terms of magnetism and why would you like it, and another proof that magnetism is a solid state business in its useful form. These are the learning objectives of the week, and as usual we are going to discuss all of this material in our live session. See you soon!